Good afternoon, all. Thank you for the opportunity to share with you the role of disruptive technologies in building a bio-based economy in South Africa. I am Dr. Ghaneshree Moonsamy, a senior researcher at the CSIR. So a brief outline of my presentation includes a background and overview of what a bioeconomy is and how bio-based technologies can actually contribute to its development. I'll speak of a few platform technologies that we are involved with at the CSIR, and thereafter just some concluding remarks. So just for some background, bioeconomy development leverages on biotech innovations, and it's defined as the production of renewable biological resources and the conversion of these resources and waste streams into value-added products. Examples of these include food, feed, bio-based products, and bioenergy. Certain governments have pursued this avenue of economic development quite actively, and these are generally countries that have an abundance of natural resources, such as Brazil, India, and Romania. So the need for this technology development is based on a global drive for environmental sustainability, addressing climate change, and reducing our dependence on fossil fuels. Therefore, we need to develop new industries and also reintegrate technologies into existing industries. The potential impact for these technologies includes new SMME creation, economic growth and development, job creation and reduced unemployment, technological catch-up by improving the SET environment, as well as the export of goods and services versus raw materials. These technology developments have a high significance and relevance to the Sustainable Development Goals and speak to at least 14 of these 17 development goals. So the CSIR is involved in developing disruptive bio-based technologies. The term disruptive biotechnology is derived from classical innovation concepts and describes how new technologies significantly alter, change, modify conventional traditional practices. The term disruptive biotechnology is derived from classical innovation concepts and describes how new technologies can significantly alter or change conventional or traditional practices. More chemical industries are replaced by greener, more sustainable practices. The first platform is on the bio-based chemicals, and the concept involves the sustainable production of a portfolio of compounds. These provides alternative routes for producing chemicals and also involves the development of novel bioconversions. The requirements for change is that the waste generated from these chemical industries cannot readily be used. Therefore, the only option for disposal is going to landfill. The cost of disposal is therefore very expensive, and hefty fines are also incurred by the industry if discharge does not meet regulation standards. Therefore, they have very limited circular technology possibilities. The opportunity for bio-based chemical production involves the use of a portfolio of production leads that can be generated depending on the feedstock. Waste substrates can be used as a raw material, and new avenues of production could be generated. This would enable local manufacture for bio-based chemicals and polymers. The market overview is that the global green chemicals and product market size is projected to reach $97.2 billion in the next 3 years. The uniqueness of this platform technology is that key bioprocessing bottlenecks can be retrofitted to enable the development of techno-economically feasible manufacturing processes for bio-based chemicals and biopolymers in the country. The key drivers are enabling policies for synthetic chemical production, global megatrends that demand bio-based products, and the prediction is that at least 50% of chemicals will be produced using renewable feedstocks by 2050. The opportunity for the country is that South Africa has an abundance of renewable feedstock availability, and redirection of existing feedstocks from the paper and pulp industry as well as the sugar industry could be used for the local manufacture of bio-based products. This would enable new product development as well as import replacements. So the value proposition for the CSIR in these particular technology solutions is that early stage research from higher education institutes could be developed further. In addition, technology in licensing can be achieved, and local product and process development could also occur in order to develop production processes for bio-based chemicals. This would enable the CSIR bio-based platform to be an African hub for disruptive bio-based technology and product development. So for an example, a particular platform chemical such as lactic acid could be used in product and process development, whereby we can optimize and scale up a particular production process and thereafter validate this technology in a laboratory and a pilot environment. Once the technology has reached a certain maturity level, it could then be commercialized. This technology could be integrated into an existing industry or new industries could be created. This would result in a technology being developed based on a specific industrial need, and strategy-directed research and development would allow a technology to be matured along the value chain. So a technology map would generally include the sourcing of a particular feedstock. This could be an industrial waste stream or effluent that could be used. Process design would then entail either synthetic biology or feedstock extraction using novel bioprocess technology. Thereafter, synthetic biology could be done in order to develop designer microbes. This would enable a suitable, possibly even novel bioconversion process where you would have a biological production of a platform chemical and thereafter convert this using chemical processes. Potential areas of application may include pharmaceuticals, personal care, and others. The benefits and opportunities of this platform technology is that high-value chemicals and biological materials using a combination of biotechnology and chemistry know-how, environmental remediation, industrial waste valorization, and several others. The next platform would include agricultural and industrial biologicals. Agriculture is a key economic activity in the country and accounts to approximately 2.5% of our GDP. It also employs at least 5% of the population. Our primary outputs include fruit, grain, vegetables, and nuts amongst livestock. There are, however, several challenges experienced by industry, and this includes drought, losses due to pests, variation in climate, amongst others. The currently used technologies to circumvent some of these challenges include chemical pesticides, traditional fertilizers, and antibiotics. Bio-based agricultural agents includes a wide range of microbials, plants, insects, and other biological materials, and proof of this application has existed since approximately 300 AD. Negative effects of commonly used pesticides and consumer resistance has forced agribusiness to change strategy. Biological solutions can be tailored in order to develop or improve existing technologies. Agrochemical companies have also moved to adopt biological agents for use in agriculture. The benefits of these bio-based solutions include field trials with demonstrated efficacy and an increase in support and adoption of these bio-based products. There's also a stimulus of local technology development, increased affordability, and improved efficiency. Increased yields have also been noted with a greater level of sustainability. In general, product categories are split into biofertilizers, which improve the soil quantity. Product categories include biofertilizers, which improve soil quality, biostimulants, which enhance nutrient use and efficiency, as well as biopesticides, which are used as a source of biocontrol. A biocontrol technology has been developed wherein a single strain wild-type bacillus organism has been formulated into a stable spore product with efficacy demonstrated in actual field trials. A biostimulant product has also been developed containing 3 wild-type bacillus organisms that work together in a consortium. Production of these individual organisms has been demonstrated at manufacturing scale. Efficacy has also been demonstrated in actual field trials, and an 85% increase in crop yield has been noted. The next sector of application includes bio-based polymers. The construction industry is assessing alternative options to modify structural properties of subsurface soil. These properties include strength, volume stability, durability, and permeability. Microorganisms are able to produce metabolites as products. These include enzymes, endospores, extracellular polysaccharides. These biomaterials can be used as alternatives to chemical soil stabilizers such as cement and lime in order to develop more sustainable road infrastructure. Applications include biocement production, additives for rural road development, and brick and block additives. The CSIR technology to date has resulted in a single organism that has been identified to hyperproduce these biopolymers. Process development was undertaken in order to cultivate this microorganism in a lab bioreactor and thereafter extract the product of interest. This product was then subjected to application testing, where both medium and high-strength tests were conducted. Tests included resistance to abrasion and erosion, water absorption, and compression force testing. The soil types that were assessed include weathered granite, dolerite, and fly ash. Upon assessing the type of interaction of the biopolymer and the soil material, one could see that a bond was formed between two grains of sand. R&D to date has resulted in a technology demonstrator that is currently under review at a technology readiness level of 6. The next sector of application included industrial effluent treatment, as there was a direct need to remediate both domestic and industrial wastewater, as well as remediate industrial effluents. Research activities were conducted to isolate, screen, and characterize indigenous microorganisms that were then subjected to lab-scale development in order to produce these organisms. The efficacy of these organisms were tested in a lab scale and thereafter in field testing to assess performance. Once the technology was developed up to a TRL level 9, commercial implementation occurred, and the technology was licensed to a local SMME. Probiotics is another area of application, and the principle is that live organisms, which when administered in adequate amounts, confer a health benefit to the host. The mode of action typically is for an antibiotic replacement, could work as a feed additive or in disease control. Typically used organisms as probiotics include Bifidobacterium, Lactobacillus, or Bacillus species. So the Broiler probiotic was developed based on an industry need, as there are several existing challenges that are faced by a broiler producer. This includes high stocking density, the excessive use of artificial growth promoters, heat stress, ammonia generation, as well as high mortality rates. The use of probiotics suitably addresses these challenges in that it provides an alternative treatment technology to increase feed conversion ratio, improve the average daily gain, and increases resistance to disease. It also inhibits colonization and proliferation of pathogenic organisms. It lowers the mortality rate and is also a cost-effective additive. The technology was developed under a similar basis as the industrial effluent technology, whereas organisms were isolated based on their ability to perform against specific characteristics. The biosafety of these organisms were assessed, and a consortium containing a different number of organisms were developed. Bioprocess and product development, technology development occurred in tandem with market development. This resulted in a multi-mode, multi-strain probiotic that delivered a holistic effect instead of using single individual organisms to deliver a probiotic effect. This technology development resulted in the product being integrated into commercial farming practices. It demonstrated our ability in developing a tailor-made, uniquely African probiotic product. It stimulated local manufacturing and technology localization. It reduced our dependence on imports and long lead times for delivery, and also created export opportunities for our probiotic product. This technology is currently at a TRL level 6. To conclude, examples of real and relevant disruptive bio-based technology solutions developed at the CSIR has been showcased. Individual technologies are at differing technology readiness levels, and we have given evidence of our concept to commercial approach. Based on our unique offering and our centers such as the BIDC, BIDF, and NIDF, our labs and infrastructure are available from concept to manufacturing scale. There are several advantages or there are several impacts of this disruptive bio-based technology development, and this spans from increased collaborations from higher education and training institutes to job creation and circular economy development. By undertaking this type of research, we can show how to build a high-impact bio-based economy in South Africa. This map shows you the interlinks between biotechnology and other emerging areas of research and development, and one can see the impact of these disruptive technologies and the potential impact that it could have when implemented. This research is clearly aligned with the bioeconomy strategy of South Africa, as well as the Fourth Industrial Revolution initiatives. With the foresight, South Africa could place emphasis on waste valorization and promote circular economy development. Continued R&D investment in disruptive biotech innovations is imperative in order to drive RSAs. Continued R&D investment in disruptive biotech innovations is imperative and is key in driving South Africa's bioeconomic growth. And with that, I'd like to end and I'd like to open the floor for questions. Thank you.